Hello everyone! In this ROS2 lesson, you will learn how to develop a 3D model of a robotic manipulator with 6 degrees of freedom. Then, you will learn how to write a launch and URDF file that will enable us to visualize and simulate the motion of the robot in ROS2 and RViz simulation software. Here's the robotic manipulator that we will learn how to model in this lesson. It has 6 degrees of freedom. This is the first degree of freedom. It's the rotation around this axis. Then here is the second degree of freedom. It's rotation around this axis. This is the third degree of freedom, rotation around this axis. Then we have the fourth degree of freedom, and that's rotation around this axis over here. Then we have the fifth degree of freedom, and that's rotation around this axis. Then we have the sixth degree of freedom, and that's the rotation that you can see over here. That is the rotation around this axis. And in addition to this, we have also modeled the gripper. You can see that I'm moving the left finger and the right finger. I can completely close them or completely open. This is the completely closed position, and this is the completely open position. Over here, I'm using a joint state publisher to control my robot. That is, I can independently move every joint, and I can explore the envelope of the robot. Here's the URDF file that describes the kinematics chain and geometrical description of the robot. The URDF stands for Unified Robotics Description Format. This is a very important file that you will learn how to write in this video tutorial. And in addition to this file, we have another very important file. This is the so-called launch file. This file is used to represent and run this model in ROS2 environment, as well as to visualize the robot motion in RViz. RViz is this software that I'm using to visualize the motion of the robot. In this lesson, we develop a basic URDF CAD model. In the future tutorials, we will explain how to simulate the dynamics and motion of this robot in Gazebo and MoveIt programs. This lesson is developed under the assumption that you're using ROS2 Humble Hackspill and Ubuntu 22.04. The modeling procedure is thoroughly explained in this tutorial, and you have to carefully follow every step of this tutorial in order to properly implement the model. This lesson is also accompanied by a step-by-step manual, URDF and Python files. A link to the manual and files is given below. Okay, let's start with modeling. The first step is to check the Linux and ROS2 distributions. For that purpose, open a new terminal. And in this terminal, you need to write and execute this command. As the output, you should see Ubuntu 22.04. If you see this version of Ubuntu, where this last number really doesn't matter, this means that you have proper Linux distribution and you can continue to watch this video tutorial. If you don't have this Ubuntu distribution, I strongly suggest you that you install it. Okay, next, let's verify our ROS2 version. To do that, you need to write and execute this command. This command will source the ROS2 environment. And after that, you need to execute this command. If you see Humble as the output, this means that you have the proper ROS2 version. Although I developed this tutorial for ROS2 Humble, everything explained in this tutorial can be easily generalized to other ROS2 distributions such as Iron or any other distribution that appears after April 2024. Next, we need to install the necessary packages and programs. First, let's close the original terminal. Then, let's open a new terminal. I'm asking you to open a new terminal in order to teach you the following. Every time you want to do something in ROS, you need to source the environment. Okay, so let's do that. Again, open a new terminal, and let's start with modeling. Over here, I will change the size of my terminal window, and I will adjust the size of this manual such at the same time you can follow the manual and see what's written over here. Let me just expand this. Perfect. Okay, again, the first step is to source the environment. To source the environment, you need to execute this command. Okay, next, let us now install the necessary programs and ROS2 packages. Before you do anything, it's very important to update the system and to install gedit. Okay, so let's update the system. First, we need to type this. Then you need to enter your password. This will take some time. Okay, then you need to upgrade by executing this command. Yes. And here, of course, you need to be patient since the complete system is being upgraded and updated. This will take some time. And finally, we need to install gedit editor. This is a very powerful and simple editor for quickly editing Python, URDF, or C++ files. Okay, you can see over here that gedit is already installed in my system. However, in your case, you will see the installation progress. Next, we need to install several ROS2 packages. I will explain these packages later on in more details. However, for the time being, let's install them. First of all, let's install ROS Humble Robot State Publisher. As you can see over here, this package is already installed in my system. However, in your case, you might see the installation progress. Next, we need to install Joint State Publisher. Okay, then we need to install Joint State Publisher Graphics User Interface. And finally, we need to install this package called Zacro. We will not be actually using Zacro in this tutorial. However, in our future tutorials, we will be using Zacro. Let's now explain these packages. The first package is the Robot State Publisher. This package takes joint angles or displacements as inputs and publishes 3D poses of the robot links using a kinematic tree or the kinematic chain of the robot. The state of the robot is published to TF2. TF2 is a transform library that's used to keep track of the relationship between coordinate frames over time. It maintains a tree structure describing the relationship between the coordinate frames. Also, this library enables us to transform vectors, points, or any quantity between any two coordinate systems. Then, we installed Joint State Publisher. This package is used to publish joint states. It publishes messages of the type sensor messages joint state. Then we installed Joint State Publisher Graphics User Interface. This package is used to graphically set and publish joint state values for a given URDF model. We will explain Joint State Publisher Graphics User Interface later on in this tutorial. And finally, we install ROS Humble Zacro. This is a package for using Zacro macro language. I will explain how to use Zacro macro language in my future tutorials. Next, we need to verify that RViz visualization software is installed. RViz should be installed together with ROS2. However, it's always a good idea to verify that this package is installed. For that purpose, we will execute this command. And we can see the path of RViz. It's located over here. Next, we need to create the workspace and the package. And let's again close this terminal and open a new terminal. We're doing this in order to practice the sourcing of the environment. Okay, so let's expand this menu such that you can see what I'm typing and at the same time follow the manual. Once you open the terminal, make sure that you're in the home folder. You can do it like this. And let's source our ROS2 environment. By doing this, we create the so-called underlay. Next, let's create the workspace folders. By executing this command, we will first create WS Manipulator folder, and in this folder we will create the source folder. Next, let's create the package. To create the package, we need to navigate our current location, or better to say, to change the current location to the source folder. In this source folder, we need to create the package, and we do it like this. ROS2 package create. This is the standard parameter, as well as this one. And here is the main part. This is the name of our package. It's going to be called Manipulator. Okay, let's continue. Next, we need to create several folders. To do that, we need to go to this folder. And in this folder, we need to create 3 folders. The first folder is the launch folder, the second folder is the URDF folder, and the third folder is the config folder. Let's see the newly created folders. Here they are: config, launch, and URDF. Besides these folders, you see several other folders over here. However, these folders are not important in the current application. The launch folder will contain the Python launch file that's necessary to run the model in RViz. The URDF folder will contain the URDF source file of the model. Note that URDF stands for the Unified Robotics Description Format. This is a file format that's used to specify the geometry of robots and some other properties. And finally, the config folder will be used to store the RViz configuration file that we will automatically create. Let us now build the complete workspace. We will execute the build command several times in this tutorial. When you want to build the package or your workspace, you need to navigate back to the workspace folder, that is to our original folder, and in that folder you need to execute this command, build. Okay, let's continue. The next step is to create the URDF and launch source file. First of all, let us go to the newly created URDF folder. We do it like this, and in this folder let's create the file called model.urdf. Here's how we do that. We call gedit, and here is our file. Over here we will write the URDF description of our model, that is, we will define the visual representation as well as the kinematic chain describing our robotic system. To make this video tutorial as concise as possible, over here I simply copied and pasted the URDF file. And I will explain this file line by line. Here's the first line. Over here we are specifying the XML version, and this is a standard line for any URDF file. This is how we write comments. So this line is just a comment. The comments start like this and they end like this. That is, this is the beginning of the tag and this is the end of the tag. This is the classical XML language. Over here, we open the robot environment or the robot tag. We specify the name of the robot. I will call the robot as Robot Manipulator, and since we open this environment or this tag, we need to end it at the end. And here's the end. So when you start working with XML files, And with URDF description, you will start with this line and you will end the environment at the end of your file. Everything between begin robot and end robot is the CAD and kinematic chain description of your robot manipulator. Over here, I'm defining the colors that are used later on. I specify the blue color and I specify the RGBA code for such a color. I'm choosing 0 for red, 0 for green, and for blue 0.8. And over here I'm specifying the transparency. Then this is the code for red, 0.8, 001. This is green. This is yellow. And this is the RGBA code for the cyan color. Next, we need to define the links and joints of our robot. That is, we need to define a kinematic chain and the CAD representation of our robot. Here's the kinematic description of our robot. The robot consists of links and joints. Let's start by analyzing this figure. We have a base link. This is the red cylinder over here. Then we have link 1. This is the yellow cylinder over here. Then we have link 2, the red cylinder. Then we have link 3, the yellow cylinder. Then we have the link 4, the blue cylinder. Then we have this link 5 over here. Then we have the link 6, which is this red cylinder. And then we have the link 7 over here. That's our one finger, and another finger is the link 8. You can see the finger links over here. This is the link 7 and this is the link 8. Two links are connected to each other by joints. Here's our first joint. This is the fixed joint. Then the base link and the link 1 are connected by joint 1. Joint 1 is the rotational joint. In the URDF terminology, rotational joints are called revolute joints. Consequently, joint 1 is a revolute joint. Then, link 1 and link 2 are connected by using again a revolute joint. This is joint 2. Then again, link 2 and link 3 are connected by joint 3, and joint 3 is again the revolute joint. Then we have joint 4 over here, which again is a revolute joint. Then we have a joint 5, which is also a revolute joint. We have joint 6, which is a revolute joint, and we have two additional joints, one over here and one over here. These joints enable translational motion of our fingers. In ROS2 and URDF terminology, translational joints are actually called prismatic joints. This is our end effector. The first finger will translate in this direction and the second finger will again translate in this direction. Consequently, we have two prismatic joints, joint 7 and joint 8. Here we need to explain several important conventions that are used by RViz and ROS2. You can see that there is a coordinate system attached to every joint. Here is the coordinate system. This is the y-axis, and usually the y-axis is represented by the green color. Then the z-axis is represented by the blue color. And over here the x-axis you cannot actually see since it's covered by the link. However, the x-axis is represented by the red line. You can see it over here better. This is x, this is y, and this is z. And over here, if you go up, you can see, for example, for this joint over here, you can see the z-axis, here it is. Over here for joint 4, you can see the z-axis over here, and you can see the y-axis. And you can also clearly see the x-axis. This is the x-axis. Again, when you see green, this means y. When you see blue, this means z. And when you see red, this means x. Next, it's a standard convention in robotics that the rotational axis of the joint is always Z. And to follow that convention, that is to respect the standard way of describing axis, we have placed the rotational or revolute axis always as Z, and we have rotated the coordinate system such that the Z axis is always the axis around which we rotate our robotic system. And you can see, for example, this first base link is rotated around this blue axis, that is around Z axis, that is the rotation is like this. Then we have link 2. Link 2 rotates around the blue axis, that is around the Z axis. Then link 3 rotates around the blue axis, etc. This is a very important convention to understand. If you understand this, then you will not have any problems to model your robot. Okay, let's now learn how to represent this kinematic chain by using the URDF file. We stopped over here, that is, we defined all the colors. Over here, we need to add the dummy world link and a fixed joint to fix the robot to the world. This is actually not very important for the RViz simulation, however, this is very important later on for the Gazebo simulation. And first of all, we need to define our link name. That is, we need to define our world link, which is actually not represented over here. Here's how we define a link. We start the link tag and we end the link tag. And that's it. And we are not specifying anything anymore about world. Then we need to specify our first joint. How do we specify joint? Well, we start the joint tag or joint environment. We specify the name of the joint. The name of the joint is the fixed joint. The type is fixed. We specify the origin. Here RPY stands for the roll, pitch, yaw rotation. This is the rotation around X, Y, and Z axis. And this is the translation of the coordinate system. I will explain thoroughly this later on. Then we need to specify the parent link and we need to specify the child link. The child link is this dummy world link, and the parent link, actually other way around, the parent link is this dummy world link and the child link is the base link. Now looking at this kinematic chain, this is the base link and it's a child of our joint. This is very important. Now I will scroll one slide down to show you what's happening. Where is our fixed joint? Well, its coordinate system is actually located over here. Its child link is actually base link. And this is a simple dummy joint that's used to fix our robot to the world. Next, let's learn how to define a real link. Over here, we will define the base link. The base link is this base of the robot. And here is the 2D representation of the base link. How do we define a link? We start the link environment and we end the link environment. Over here, we define the visual representation of our link. We start the visual tag and we end the visual tag. Over here, we specify the geometry of our link. It's a cylinder with a length of 0.2, and this is the length in direction of the z-axis, and with a radius of 0.4. That is, the diameter is 0.8. Next, we need to specify the origin. What is this origin of the link? Well, this is basically the displacement and rotation of the center of this link with respect to the coordinate system of its joint. And this is very important. Over here, we don't have roll, pitch, and yaw rotation of the coordinate system, and we don't have translation. That is, we will place the center of our link exactly at the center of the fixed joint, and this is very important. Then we specify the material, and the material is green. And this is actually the parameter that we defined over here at the beginning of this file. Okay, next we need to specify joint 1. Here's joint 1 in this 2D representation, and in the 3D representation, joint 1 is over here. It's between link 1 that we need to define and base link. Okay, so again, how do we define joint 1? We start the joint environment and we end the joint environment. We specify the name, the type is revolute, we specify the parent link will be base link, the child link will be link 1, and we need to specify the origin. Okay, to understand how to specify the origin, let's go back to the 2D representation. And let's see. Here we need to specify the center of the coordinate system representing our joint. And this center is represented with respect to our previous fixed joint. That is, to the previous joint in the kinematic change. That is, when I say over here, for example, 0.1 in z direction, this means that I'm actually placing joint 1 coordinate system 0.1 with respect to this coordinate system in the z direction. This is very important. So it's always the case, when you define the origin of your joint, you always define that origin with respect to the coordinate system of the previous joint. And let's see, we don't have any rotation and we only have translation in the z direction for 0.1. And note over here that 0.1 is actually half of the length of my base link. Next, I need to define the effort and velocity. These parameters are not very important for our current simulation. However, they might become very important if you want to simulate this robot in Gazebo or in MoveIt. However, these bounds are very important. I need to specify the lower and upper rotational angle bounds. Over here, this number is actually represented in radians. This is actually minus pi and plus pi. That is, I want my joint to be able to move from minus pi to pi. That is, from minus 180 to plus 180 degrees. That is, I want to enable full 360 degrees of rotation. Okay, let's continue. Next, we need to define link 1. And note over here that the child of this joint is actually link 1, that is this link. Let's define this link. Again, visual representation, geometry, it's a cylinder, length 0.6 and the radius 0.15. And now, this is very important, we need to specify where is the center of this link with respect to joint 1 coordinate system. We can see that we are placing the center of this link at 0.3 in the z direction, and we don't have any rotation, and we only have a single translation. That is the translation for 0.3 in the z direction. And finally we specify the color, we end visual, and we end link, and that's it. Next, we need to specify joint 2. Joint 2 is located over here, and it connects link 1 and link 2. And you can see the coordinate system of joint 2. Joint 2 should rotate around the z-axis, and it should have another important property. That is, it should be translated with respect to the coordinate system of joint 1. Okay, now one thing I forgot over here is this part over here. Whenever you specify joint, in this case joint 1, we need to specify the axis of rotation. And over here the axis of rotation is the z-axis. And that will always be the convention in this tutorial. That is, the axis of rotation will always be z. This is very important. Okay, let's proceed with the definition of joint 2. Let's see. Here is the coordinate system of joint 2. First of all, this is revolute type of a joint. That is, we want to have rotation. We specify the name. Then we need to specify the parent link. The parent link is link 1. The child link is link 2. And we need to specify the origin. And here you have to be very careful what's happening, since we want always to keep the convention that our joints are rotating around the z-axis. Consequently, we need to define the rotation and translation between joint 1 and joint 2. Okay, these coordinates are representing the rotation and translation with respect to the coordinate system of the joint 1. We can see the following. We don't have rotation around the x-axis. However, what do we have over here? We have a negative rotation around the y-axis. So let's see again this graph over here, and let's identify the coordinate system. So here's the coordinate system of joint 1. This is y. This thing is over here, x, and the z over here you cannot see. However, you can see still a small blue circle over here. Now, what do we need to do? To make sure that we always have rotation around the z-axis, we need to rotate this coordinate system around the y-axis, and the rotation should be negative for this number. This number in radian is actually pi over 2, and that's 90 degrees. So by rotating this coordinate system for 90 degrees, we will actually obtain that the z-axis is oriented like this. Okay, and in addition to that, if we see this graph over here, we need translation. That is, this coordinate system should be translated with respect to this coordinate system. So in the x-axis, we have minus 0.15. And again, this translation is represented in joint 1 coordinate system. We have minus 0.15, and in the z-axis direction, we have 0.05, and you can see it over here. Next, we need to specify that this joint will rotate around the z-axis, so we need to specify 0, 0, 1. We specify the effort, velocity, and the lower and the upper bounds, and that's it. And then we end the joint. Next, we need to define link 2. Here's the visual representation. It's again cylinder with a length of 1 and with a radius of 0.1 or the diameter of 0.2. Next, we need to specify the center of this link, and here's how we specify the center. Let's first resolve the rotation, actually the translation. We see that in this coordinate system, that is in joint 2 coordinate system, the center of this link is placed at 0.3 in the x direction, 0 in the y direction, and the z direction. What do we have in the z direction? We have 0.1. And here will be the center of this link. And this is very important. However, we have a rotation over here. We have the rotation around the y-axis of joint 2 coordinate system. So let's see this graph over here. Here's joint 2. And we need to rotate the standard coordinate system of links for the angle of 90 degrees. 90 degrees in radians is given over here. So why we do that? Well, when you define a link, the link will automatically be extruded in the direction of the z-axis. That is, if you didn't have this rotation, this link 2 will go in this direction. The link will be along the z-axis, similarly to this link 1 that goes along the z-axis. Consequently, you need to introduce this rotation. And over here we specify the color. The color is red, and we end the visual, and we end the link. Now, by using this principle, we can specify all other joints and all other links. Let's start with joint 3. Here is the coordinate system of joint 3, and I will zoom it over here such that you can see it better. So joint 3 is over here, or if you like to see on the other graph, Joint 3 is represented over here. Okay, again, this joint connects link 2 and link 3. It is of type rotation, that is revolute. The parent link is link 2, the child link is link 3. Where is the origin of joint 3 with respect to joint 2? Well, let's see what do we have here. We only have the translation around, or actually along, the x-axis for 0.7. That is the distance from here to here in the x direction of joint 2 coordinate system is 0.7. And again, we need to follow the convention, making sure that the rotation is always around the z-axis, and we specify the axis of rotation. Then we specify the effort, velocity, and lower and upper bounds for our rotation. And that's it. Next, we need to specify link 3. Again, name, geometry, length will be 1, radius 0.1, and again, we need to specify the center of this link, however, with respect to the joint 3 coordinate system. Again, we have rotation to make sure that this link is actually extruded along the x-axis, and we have the translation, and here is the translation. This thing will make sure that the center of link 3 is actually located over here, and such that everything is properly oriented. Next, we need to define joint 4, and here is joint 4. The axis of rotation of joint 4 is given over here. Let's see. Type revolute, parent link is link 3, child link is actually link 4, the blue link over here. Where is the origin? Origin is at 0.00 for RPY, that is no rotation, and we have translation with respect to joint 3. We can see that joint 4 is located over here, and this translation is actually 1 in the x, in this direction, 0 in the y direction, and in the z direction, and the z-axis of joint 3 is over here, is actually negative. And I will zoom in so you can see it better over here. Let's repeat this once again. Let's see, we don't have rotation, however we have translation. This is joint 3, and we can see the joint 4 is 1 in the x, 0 in the y is 0 in the y, there is no displacement along this green line, and we have in the z direction for minus 0.1. 0.1 is actually the radius. This is very important. Okay, now we specify link 4. This is the blue link over here. Geometry, cylinder, length, radius. This is very important. And we specify the origin. Where is the origin of this link, or better to say the center of this link with respect to joint 4? It's simply displaced for 0.1, and that's it. And we specify the color. Let's continue with joint 5. Where is joint 5? This green line is actually the y-axis of joint 5. This small part over here is the part of the z-axis of the joint 5. And let's see. The parent link is link 4, the child link is link 5. Where is the origin? We have again rotation for the origin and displacement of the origin. And note again, this rotation and displacement is actually defined in the coordinate system of joint 4. And finally, we need to follow the convention that 0, 0, 1. This will make sure that the rotation is around the z-axis. Okay, we specify the effort, velocity, and lower and upper bounds. Next, we need to define link 5. Here's link 5. Length, radius. Then we have no rotation of its center. and we have a displacement of the center in the coordinate system of joint 5. That's it. Finally, we define joint 6. Here's the joint 6. You can actually see it on the other graph. Let me zoom out. Here's the joint 6. It's located over here. The z-axis is this axis. This means that this red link over here will rotate around the blue axis over here. The parent link is link 5. The child link is link 6. And you can maybe see it even better over here. The child is link 5. The parent is link 5. The child is link 6. We have rotation and we have translation. We specify the axis, we specify the effort, velocity, lower and upper bound. And finally, we specify link 6, the length of the link, the radius of the link, and we have the center is displaced. That is, we have translation of the center in the coordinate system of joint 6. And that's it. Now, we need to model our gripper. That is, we need to model the gripper fingers. How do we do that? Well, relatively simple. First of all, we need to define the joint of this left finger of our gripper. The joint name is joint 7. Its type is prismatic. This means that we want to have a translation over here. What is our parent link? The parent link is link 6. What is the child link? The child link is actually link 7. That is, the finger will be a link, and we will define it over here. And we need to specify the origin. So where is the origin? I'm basically placing the center of joint 7 at the base of this box over here, or better to say, of this rectangular object. What do I have? I don't have RPY, rotation of joint 7 with respect to joint 6. However, I have the displacement. And let's again look at the global picture. Joint 6 is actually located over here. That is at the base of this blue, or actually of this red cylinder. And in order to define the joint 7, I need to have translation. And here is the translation. I'm specifying the effort after that, velocity, lower and upper bound, and I'm over here specifying the translation. Since this will be a translational or prismatic joint, I selected that the translation is in the direction of the x-axis. That is, the translation will be along this axis. You can notice over here the lower and upper bounds. This is very important. Next, I need to define link 7. Link 7 is my left finger. It's a box. This is the dimension in the x, this is the dimension in the y, and this is the dimension in the z direction. Then I need to specify the center of my box with respect to joint 7, that is with respect to the coordinate system of joint 7, and the center is placed over here, and this is material. Similarly, I define joint 8. Joint 8 is placed over here. Again, it's a prismatic or translational joint. Its parent link is link 6, its child link is link 8, and link 8 is actually this right finger. And over here, I'm specifying the rotation and translation of this joint with respect to the joint 6. Actually, with respect to the joint 6. This is very important to understand, since the parent joint is actually joint 6. Okay, so let's see what do we have over here. The axis will be x, right? We need to make sure that the translation is along the x-axis, and we specify the lower and upper bounds. And finally, we define link 8. This is our right finger. We specify the geometry, x, y, z box dimensions, and we specify the origin. That is the center of this box location with respect to the coordinate system of joint 8. And we specify the material and that's it. We end visual, we end link, and we end our file. Don't forget to save this file by pressing Ctrl S. Again, I will go from the beginning and I will show you the file, line 1, line 29. Then line 29, line 54. Then line 54, line 79, line 79, line 106, line 106, line 133, line 133, line 160, one line 160, line 186, and one line 186, line 194. That's it. Now you can safely close the file. Next, we need to add the dependencies. For that purpose, we need to go to this folder, and in this folder, there is one very important file. The name of this file is package XML. Let's edit this file. We need to add several lines to this file, and here are the lines. You can add them over here, for example. After this, test dependency. Here the executable dependency. Over here we are saying that our package should depend on other ROS2 packages. The first package is Joint State Publisher, then Joint State Publisher Graphics User Interface, then Robot State Publisher, then Zacro and RViz. Save this file and close it. Next, we need to create the launch file. To do that, we need to go to the launch folder and we need to create the launch file. We do that by creating the file. I will erase this since this is the error. The file name should be display.launch.py. Here it is. Again, to make this tutorial as short as possible, I will simply copy and paste the content of the display.launch.py file. And over here I'm using gedit to create this file. However, I strongly suggest that you use, for example, Spider, Anaconda, or VS Code to edit Python files. The issue with gedit is that sometimes you might have the issue with tab width. You can see that tab width is 4, and this might not be always necessary and might create some issues with compiling the file. Consequently, the idea is, and my suggestion, that you use VS Code or, for example, Spider to edit Python files. Okay, let's explain this file. First, we need to import the necessary libraries. We import launch. Then, from launch.substitution, we import command and launch configuration. Then, we import launch ROS and we import OS. Over here, we define a function that will generate the launch description of our package, and we will be able to run the complete software and the package as well as the visual representation by only running the display.launch file. Okay, so what's happening in this function? This function will actually return the launch.description object, and we need to define all the parameters. Let's start. First of all, we need to define package path. We are using launch ROS substitutions, find package share. Here's the name of the package, Manipulator, and we are finding the folder Manipulator. And this will give us the path of the folder Manipulator inside of our workspace. Then we need to specify the path of our URDF model. This should be the absolute path. Over here we define the path of our Manipulator folder, and inside of this folder there is a folder called URDF, and inside of URDF there is a file called model.urdf, and you can verify that by doing this. Go to home, locate your folder, then you need to locate the source, and here's the path. you can see the complete path with respect to the home folder. And that's precisely this path over here. Then on top of that path, we need to add URDF model.urdf. Again, we have the URDF folder, and in that folder we have model.urdf file. And that's precisely what's happening over here. We are specifying the URDF model path. Then we need to specify a path to the RViz configuration file. Again, going back here, inside the manipulator there is a config folder, and currently this folder is empty. However, I will show you later on a trick to create this file. Although this file doesn't exist currently, let us include this file. It will not create any issue if this launch Python file cannot locate this file. Over here I'm printing the URDF model file just for verification. You don't need this path. Now I'm opening my model and I'm reading the robot description. I'm storing it over here. Then I'm creating this dictionary. I'm specifying the key to be robot description and the value to be actually my URDF file. So over here I read the URDF file and I created a dictionary called params. Then over here I need to create my robot state publisher node. I'm calling this function from launch ROS actions node. The package is robot state publisher. The executable file is robot state publisher. The output should be screen. And look here what happens. Here are the parameters. And that's exactly our model. Better to say a dictionary representing our model. And here are the arguments, basically the path, URDF model path, the complete path. Next, I need the joint state publisher node. This is a different from robot state publisher node. Again, the package is joint state publisher, the executable file is joint state publisher, the name is joint state publisher. Here are the parameters, again, the model, and the arguments are URDF model path. Then I need to specify the joint state publisher graphics user interface node, package, executable, name, arguments, again, URDF model path, this path over here, and here the launch condition. Over here, I'm simply saying graphics user interface. Okay, next we need to define the RViz node. This is our RViz. Package is RViz2, executable is RViz2, name is RViz2. The output should be screen since we want to display the model on our screen, and over here we specify -d and we specify the path to the RViz configuration file defined over here. Again, this file currently doesn't exist, however we will create it. Okay, and over here I create launch description object. I specify declare launch arguments, name should be graphics user interface, default value should be true, and description is simple and it's arbitrary. I'm just saying over here this is a flag for the joint state publisher graphics user interface. Then what else I'm specifying over here? I'm specifying the robot state publisher node, joint state publisher node, then joint state publisher graphics user interface node, and RViz node. And again I close over here first, then I close over here, and that's it. Simple as that. Here's again my launch file, line 1 to line 30, then line 30 to the end. Simple as that. Save this file and you can safely close it. And here's the final step. But however, before we actually build the file or build the package, we need to do several adjustments. First of all, we need to go to this folder, and in this folder there is another very important file. This is the cmakelists file, and we need to edit this file. Now, how do we edit this file? Well, there is a build testing if statement, and just above this statement, that is over here, we need to add this. Over here we are saying that Basically, there are several important folders that are very important for this project. These folders are launch, URDF, and config. What will happen? Now, the build system knows that there are files located in the launch, in the URDF, and in the config folder. Save this file and close it. Okay, now we are ready to do the final build of our workspace and of our package. Again, you need to go to the root folder of your workspace, and in that folder you need to call conbuild. Okay, let's hope there are no errors. Okay. After you build everything, you need to source your new package. That is, you need to source this file. This is very important. Remember at the beginning of this tutorial, we sourced the base ROS2 environment. However, in addition to this, we need to source the setup.bash file of our newly created package. Okay, and now we are ready to launch everything. How do we launch? Well, we call ROS2 launch, then we specify the name of the package, and we specify the name of the file. The name of the file is display.launch.py, and this Python file will launch all the node, launch RViz, and create everything. So let's hope that everything will work. Press enter over here. Now, go back over here and search for the errors. And let's analyze what's happening over here before we actually look into the RViz. Okay, let's see. We have that robot state publisher that is started. Okay, join state publisher node is started. Join state publisher graphics user interface started. RViz started, and we have infos. We can see that we received base link 1, 2, 3, 4, 5, 6, 7, 8, 9, perfect, and the world, and we see some other messages. No errors. This is very important. Let's see our RViz. Nothing happens. Why is that? Well, if you now go back to your launch file, and we can easily find the launch file over here, you will see that there should be some configuration file for RViz. However, we don't have that configuration file first time we start RViz. However, we can adjust RViz such that we can display our model and create that file such that next time you run the package, you will actually see the model immediately. Okay, so let's make a few adjustments. First of all, click on Add, click over here on Robot Model, then over here under the description, make sure that robot description is selected, and you can see already something over here. However, you need to adjust the fixed frame. You need to select, for example, the world as a fixed frame, and voila, here it is. Perfect. Now, let's see our coordinate systems. You can do that by clicking over here, then click on TF, click OK, then expand over here, and for example, I always like to select marker scale S2 over here, and you can see larger coordinate systems. Okay, perfect. Now, let's save this configuration. How do we save the configuration? You need to create another file. The name of this file will be config.rviz. And if you go back to the Python launch file, you will see the name of the file. So we need to create that file. Go to RViz, click on File, Save Configuration As. Now, go to the corresponding folder, to Configuration folder, and save the current configuration. Click on Save. Okay, now let's close RViz, go back to the terminal, do Ctrl+C to kill everything, and here I clear the history such that you're not confused by the commands I'm typing. So let's run everything again. Go to the source folder, build the package. We need to build the package once again since we changed something. Let's source our package and let's run again our package. Okay, and voila, here it is. You can immediately see that RViz was able to properly load the configuration file, and you will not have to manually adjust all the settings over here. And finally, let's learn how to move our robot. You will see over here another window and another small program. And this is actually our joint state publisher. Joint state publisher enables us to control the robot. So let's control the first joint. Here it is. Here's joint 2. Here's joint 3. Perfect. Here's joint 4. Let's do something like this. Here's joint 5. Perfect. Let's rotate like this. Let's continue. Joint 6. Verify that we can move all the joints. And let's try to close our gripper. Left one and the right one. And that's it. Okay, that's all for today.